Hey guys, tonight we're going to step outside, not in the way we usually do, not to feel the cool night air or to look for constellations that we already know, but to truly leave. We'll leave our small blue island, drift past the silent witness of the moon and the rusted plains of Mars, and we're going to journey toward the very edge of the solar system. We'll brave the fierce winds of Neptune and wander through the elegant rings of Saturn, all while staying right here in the quiet comfort of your room. It's a voyage that, in real life, would take decades and would expose you to the vacuum of space and the crushing gravity of gas giants, so perhaps it's best we just imagine it all together. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. As you settle in, maybe you can share in the comments where you are and what time it is for you. Wherever you are in the world, whatever time it is, let's begin our journey as one. Tonight, we are travelers. Our story begins not with a bang, but with a whisper, a gentle collapse. Imagine a colossal dark cloud, a nebula far larger than our current solar system. This cloud was not a single solid thing, but a swirling, ethereal mix of dust and gas, mostly hydrogen and helium. For millions of years, it just floated there in the quiet interstellar medium, a vast, cold, and dark presence. But within its heart, something was happening. A tiny ripple, perhaps from the shockwave of a distant supernova, brushed past this cloud. It was a nudge so gentle it was almost imperceptible, but it was enough. This disturbance created a small pocket of slightly denser material. And in the universe, a little more density means a little more gravity. Gravity is a beautiful, patient sculptor. It works not with a hammer and chisel, but with an endless, subtle pull. That tiny, denser pocket began to attract more dust and gas. Slowly, almost shyly at first, the cloud started to collapse inward on itself. As it did, it began to spin. This is a fundamental principle of physics, the conservation of angular momentum. It's the same reason an ice skater spins faster when they pull their arms in. The more the cloud collapsed, the faster it spun, forming a flat, rotating disk. At the very center of this swirling maelstrom, all that dust and gas was being squeezed together under immense pressure. The atoms of hydrogen began to feel the incredible squeeze, getting closer and closer until they reached a point where something truly extraordinary happened. They began to fuse. This is a process known as nuclear fusion, the very engine that powers every star in the universe. It's not just a physical reaction. It's a cosmic alchemy. Hydrogen atoms merge to form helium, and in that process, an enormous amount of energy is released. The core of our nascent sun ignited, and for the first time in this corner of the galaxy, there was light. This newly born star, our sun, was still growing, pulling in more and more material from the surrounding disk. But that same disk, the protoplanetary disk as it's called, was where the rest of our story was being written. The material that didn't get pulled into the sun was left behind, a vast, diffuse ring of debris. Think of it like a cosmic workshop, with different materials scattered at different distances from the central furnace. Close to the sun, it was hot. So hot that only substances with high melting points could exist in a solid form. Things like rock, iron, and other heavy metals. This is a subtle but crucial detail. At the beginning, our solar system was sorted by temperature. The stuff that could withstand the heat stayed close, while the lighter, more volatile materials, like water, methane, and ammonia, were pushed further out. Over the next tens of millions of years, this sorted material began to stick together. Dust grains would gently collide and cling to each other, forming small pebbles. These pebbles became rocks, and the rocks became boulders. This process, known as accretion, was slow and haphazard. It was a cosmic game of billiards, where chance collisions determined the fate of these fledgling worlds. Some grew quickly, clearing their orbits of debris and becoming the dominant forces in their region. Others were consumed or shattered. In the inner solar system, where the rock and metal were, this accretion led to the formation of the 4 terrestrial planets: Mercury, Venus, Earth, and Mars. They are all small, dense, and rocky. A lesser-known fact about this period is the sheer violence of it all. Our solar system was a much more chaotic place. Imagine not just 1 or 2, but dozens of planetesimals, as they're called, the size of our moon or even Mars, all zipping around in unstable orbits. It was a shooting gallery, with collisions that could reshape entire worlds. We still see the scars of this period on the surfaces of Mercury and our moon, covered in craters from this early bombardment. It was this cosmic chaos that led to one of the enduring questions of planetary science. Was this kind of violent formation a necessity for life to begin? The truth is, we don't really know if our solar system's early turmoil was a unique prerequisite or a common event. Further out, beyond the frost line, the distance from the sun where it was cold enough for ice to exist, a different kind of planet was forming. Here, the building blocks were not just rock and metal, but also vast amounts of frozen water, methane, and ammonia. These icy cores grew much larger, much faster than their rocky counterparts. Once they reached a certain mass, something dramatic happened. Their gravity became powerful enough to pull in the vast, abundant hydrogen and helium gas that made up the majority of the protoplanetary disk. They swelled, ballooning into the gas giants we know today: Jupiter and Saturn. They are so different from us, a testament to the idea that a world's fate is shaped as much by its location as its composition. And even further still, at the very edge of the disk, the 2 ice giants, Uranus and Neptune, were born. They took longer to form, likely due to the scarcity of materials so far from the sun, and they never gathered the same immense gaseous envelopes as Jupiter and Saturn. Their formation is still a bit of a mystery, a topic of ongoing debate among scientists. Why are they so different from their larger siblings? It's one of those beautiful, unanswered questions that keeps us looking up. So in the end, we are left with a system of 8 worlds orbiting a single, brilliant star. A family born from a single cosmic breath, yet each member is utterly unique. They are a testament to the simple rules of physics, playing out over an unimaginable span of time. We have the swift messenger, the veiled goddess, the blue oasis, and the red echo. We have the great giant, the ringed jewel, the tilted wanderer, and the distant blue heart. Each one is a story waiting to be told, a chapter in our grand journey. It's a story of creation and chaos, of immense distances and the invisible forces that bind everything together. A story that, in its silent telling, brings us a new kind of peace. From the deep, dark beginnings of our solar system, we now move inward. We've seen how the grand narrative of our sun's birth created a cosmic temperature gradient, and that gradient sorted the elements, giving rise to our small, rocky inner worlds. Of these, there is one that lives a life of extremes, a world that is at once a swift messenger and a solitary wanderer, forever caught in a delicate dance with our star. We are now arriving at Mercury. Mercury is the smallest of the 8 planets and the closest to the sun. If you were to stand on its surface, looking up at the sky, the sun would appear to be more than 3 times larger than it does from Earth. The light it casts would be a harsh, unforgiving glare, and the heat would be utterly unbearable. The side of Mercury facing the sun can reach temperatures of around 800 degrees Fahrenheit, hot enough to melt lead. But here's the strange part. On the side of the planet facing away from the sun, a side plunged into perpetual shadow, the temperature plummets to a bone-chilling minus 290 degrees Fahrenheit. The difference between these 2 extremes is over 1,000 degrees, a swing so vast it defies easy comprehension. Mercury is a world of fire and ice, a paradox wrapped in rock. This dramatic temperature contrast is a direct result of Mercury's strange and unique orbit and rotation. Remember how we talked about angular momentum, the force that made our solar system's disk spin? Mercury's spin is unlike any other planet in our system. Its day, the time it takes to rotate once on its axis, is a little more than 58 Earth days. But its year, the time it takes to orbit the Sun, is only 88 Earth days. This creates a bizarre phenomenon. For every 2 times Mercury orbits the Sun, it rotates on its axis exactly 3 times. This is called a 3.2 spin-orbit resonance. It's a very unusual and specific relationship, a cosmic metronome. Think of it this way. If you were to stand on a certain point on Mercury's surface at sunrise, by the time the sun sets, a full Mercury day has passed. But by the next time the sun rises at that same spot, a Mercury year will have gone by. What this means is that one day on Mercury is twice as long as its year. This slow, deliberate rotation is what allows one side to bake under the sun for so long, while the other side freezes in the dark. It's a rhythmic, patient, and brutal cycle. The strangeness of this resonance was not even discovered until the 1960s, when radar observations confirmed it. For a long time, astronomers thought Mercury was tidally locked, like our moon, always showing the same face to the sun. We thought it was a simple, unchanging world. This serves as a humbling reminder of how much we still have to learn, even about our closest neighbors. Despite its fiery proximity to the sun, Mercury has a surprisingly gentle texture and a fascinating history. Its surface is heavily cratered, a testimony to the early violent period of our solar system that we touched on in the last part. The craters are of all sizes, from tiny pockmarks to vast impact basins hundreds of miles wide. The largest of these is the Caloris Basin, a feature so immense it's believed to have been caused by an object at least 60 miles wide. The energy of this impact was so great that it sent shock waves through the entire planet, triggering seismic events and creating a bizarre hilly terrain on the exact opposite side of the planet. It's a perfect example of a cosmic chain reaction. A pebble dropped in one ocean, creating a ripple on another. But here is where a great mystery lies. Scattered among these ancient, heavily cratered regions are smooth, volcanic plains. These plains are a much younger formation, suggesting that Mercury was geologically active long after its birth. For a small planet, one that should have cooled and hardened relatively quickly, this is a puzzle. Even stranger, the Messenger spacecraft, which orbited Mercury for 4 years, found that the planet is still shrinking. As its core slowly cools, the surface buckles and cracks, forming what are called lobat scarps, long cliffs and ridges that stretch for hundreds of miles. The presence of these young plains and the evidence of ongoing geological activity asks a profound question. What kind of internal engine could a small, dense planet like Mercury have, and why is it still running? We don't have a complete answer. It is a mystery we continue to ponder. One of the most fascinating discoveries about Mercury is the presence of water ice. You might think this is impossible for a planet so close to the sun, but remember those deeply shadowed regions, the ones that are minus 290 degrees Fahrenheit? At Mercury's poles, there are craters so deep that sunlight never reaches their floors. These craters are perpetual refrigerators, and in 2012, instruments on the Messenger spacecraft detected signs of ice within them. It is believed that this water arrived on Mercury's surface via comets and asteroids over billions of years, and once it landed in these shadowed basins, it became trapped, preserved in a state of eternal winter. The idea of water ice, the very substance that is so crucial for life as we know it, hiding in the dark, cold corners of a world of fire, is a beautiful, almost poetic irony. Mercury is a world of stark contradictions. It is the swiftest planet in its orbit, a tiny, nimble runner circling the sun. Yet its own rotation is lethargic and strange. It is a world of lead-melting heat and freezing cold, of ancient scars and strangely young, smooth surfaces. It is a reminder that even the most seemingly simple and harsh worlds hold deep, unexplained secrets within their metallic hearts. It is a place of paradox and a testament to the endless complexity of the cosmos, a complexity that is so great we may never fully uncover all of its truths. If Mercury is the swift, solitary messenger, then its closest neighbor is the veiled goddess, a world shrouded in mystery and danger. We've journeyed past Mercury's extremes, and now we arrive at Venus. From Earth, Venus shines brighter than any other planet, a brilliant beacon in the twilight sky. The ancient Romans named it after their goddess of love and beauty, believing its dazzling light to be a reflection of her grace. Yet, beneath that shimmering veil of clouds lies a world that is anything but serene. It is a hellscape of crushing pressures and searing heat, a stark warning of a planet's fate when its delicate balance is irrevocably lost. Venus is often called Earth's twin, and for good reason. They are almost identical in size, mass, and density. They likely formed from similar materials in a similar part of the solar system. For a long time, scientists wondered what lay beneath Venus's thick clouds. There was a romantic notion that perhaps it was a tropical paradise, a jungle world teeming with life, much like Earth might have been millions of years ago. The reality, revealed by probes like the Soviet Union's Venera landers, was a chilling one. They sent back pictures of a rocky, barren landscape under a dim, orange sky, and they didn't survive for long. The atmosphere of Venus is its defining feature, a thick, suffocating blanket of carbon dioxide, over 90 times denser than Earth's. To put that in perspective, the atmospheric pressure on the surface of Venus is equivalent to the pressure you would experience about a mile deep in the ocean. The air itself is not a gentle breeze. It's a hot, dense fluid that would feel like walking through a murky, pressurized bath. And those beautiful clouds we see? They're not made of water vapor, but of sulfuric acid, a corrosive, deadly mist. The acid rain that falls on Venus never reaches the ground, however. It evaporates from the extreme heat long before it gets there. This thick atmosphere is the engine of Venus's most terrifying characteristic, the runaway greenhouse effect. On Earth, our atmosphere, with its small amount of greenhouse gases, acts like a cozy blanket, trapping just enough of the sun's heat to keep our planet warm and hospitable. On Venus, this process went into overdrive. Carbon dioxide is an incredibly efficient greenhouse gas. As the sun heated the young Venus, any liquid water on its surface would have evaporated, creating water vapor, which is also a greenhouse gas. This trapped even more heat, leading to more evaporation and so on, in a vicious cycle. Eventually, all of Venus's water boiled away into space, and the carbon dioxide in its atmosphere grew so thick it trapped all the heat. This created a feedback loop that couldn't be broken. As a result, the surface temperature of Venus is a constant 864 degrees Fahrenheit, hotter than Mercury, even though Mercury is closer to the Sun. This fact, a simple comparison of two planets, reveals a powerful truth. A planet's climate is not just a function of its distance from its star, but of the very gases that make up its atmosphere. Venus is the ultimate cautionary tale, a natural experiment in planetary climate change on a truly devastating scale. It is a silent world, with no tectonic plates and no liquid water, where the winds in its upper atmosphere can reach speeds of over 220 miles per hour. But on the surface, there is only a slow, sluggish movement of air, almost like a hot, thick syrup. One of the lesser-known, yet fascinating facts about Venus is that it rotates backward relative to all the other planets. While Earth spins counterclockwise on its axis, Venus spins clockwise. It also rotates incredibly slowly. A single Venusian day, the time it takes to spin once on its axis, is longer than its year. It takes Venus 243 Earth days to complete one rotation, but only 225 Earth days to orbit the Sun. This retrograde rotation is a perplexing mystery, and scientists still do not have a definitive answer for why it spins this way. One leading theory suggests that a massive collision with a large planet-sized body early in its history may have knocked it off its original axis, reversing its spin. It's a reminder of the violent, chaotic past of our solar system that we discussed earlier. A single, cataclysmic event leaving a permanent scar on a world's very motion. This strange rotation, combined with its thick atmosphere, creates a paradoxical calm on the surface. While the upper winds are furious, the ground level is eerily still. There are no seasons on Venus, and its surface is remarkably uniform in temperature. The thick clouds and dense atmosphere trap heat and distribute it evenly across the entire planet, from the poles to the equator, and from the day side to the night side. The concept of a night and day side, which is so crucial to our understanding of Mercury, becomes almost meaningless here. The darkness of night is just a slightly less searing orange glow. The landscape of Venus is a mix of vast, smooth plains and volcanic features. Unlike Earth, which has a surface constantly being recycled by plate tectonics, Venus seems to have undergone massive volcanic resurfacing events in its distant past, burying its older craters. This raises a new question, one that speaks to the very heart of planetary evolution. Is this the normal course of a planet's life? Does an Earth-like world eventually lead to a Venus-like fate? The truth is, we don't know for sure what prevented Earth from experiencing a similar runaway greenhouse effect. Perhaps it was our distance from the Sun, or maybe it was the presence of a large moon, but it is one of those crucial, beautiful mysteries that makes us all the more grateful for our fragile blue home. In the end, Venus is not the idyllic twin we once imagined. It is a world of silent heat, a beautiful but deadly reminder that even small changes in a planet's delicate climate can have monumental, irreversible consequences. It is a world that appears as a symbol of love and beauty, but in reality is a mirror showing us a possible, terrible future. It is a world of contradictions and a lesson we must all remember. We have journeyed inward from the chaotic birth of our star to the fiery extremes of Mercury and Venus. Now we arrive at a place that feels both intimately familiar and endlessly mysterious. Our home. We are standing on the surface of Earth, a pale blue dot suspended in the vast blackness of space. It is a world of gentle paradoxes and exquisite balances, a place that, despite all odds, found a way to nurture life. We will explore the delicate systems that make our planet unique and consider the profound question of whether this fragile harmony is a common occurrence in the cosmos or a cosmic lottery win. Earth is a world defined by its atmosphere. We don't see it, of course, because it's invisible to us, but its presence is our protection. This thin, gaseous layer is what separates us from the vacuum of space, shielding us from harmful solar radiation and regulating our temperature. It is a mixture of nitrogen, oxygen, and a small but crucial amount of other gases, including carbon dioxide and water vapor. This composition is a direct result of the life that lives here, a perfect example of a feedback loop where life creates the conditions for more life. The oxygen we breathe, for example, was not always a major component of Earth's atmosphere. For the first 2 billion years, our planet was shrouded in a blanket of methane and carbon dioxide. Much like early Venus, it was the emergence of simple, single-celled organisms, performing photosynthesis, that began to slowly, painstakingly, fill the atmosphere with oxygen a process that was once a poison to most life forms, but became the very breath of a new era. The blue color of our planet, as seen from space, comes from its abundant liquid water. Water is a miracle substance. It has a high heat capacity, which means it can absorb a lot of heat without a large temperature increase, helping to regulate our planet's climate. It is also an exceptional solvent, able to dissolve a wide range of substances, which is crucial for biological processes. The oceans that cover more than 70% of our planet's surface act as a massive thermal battery, absorbing and distributing heat from the sun, while their currents act like a global conveyor belt, carrying warm water toward the poles and cool water toward the equator. Without this intricate dance, our planet's climate would be far more extreme and less hospitable. One of the more fascinating and lesser-known aspects of our planet is its internal dynamo. Deep within the Earth, we have a molten outer core of liquid iron and nickel, a swirling sea of metal. This liquid core rotates and generates powerful electric currents, which in turn create a massive magnetic field that envelops our planet. This is the magnetosphere, and it is our first line of defense against the harsh realities of space. It deflects the constant stream of charged particles from the sun, known as the solar wind, and protects our atmosphere from being stripped away. Without this invisible shield, our planet would look much more like Mars, a world with a thin, tenuous atmosphere. The aurora borealis and aurora australis, those shimmering curtains of light that we see at the poles, are a beautiful byproduct of this protection, a visual reminder of the cosmic struggle happening miles above our heads. Earth's uniqueness is also found in its geological activity. We live on a planet with plate tectonics, a system of large mobile slabs of the Earth's crust that are constantly moving, colliding, and sliding past one another. This process recycles elements from the surface to the interior and back again, building mountains, creating volcanoes, and driving the very carbon cycle that regulates our climate. It is a slow, methodical churn that has shaped our continents and created the varied landscapes of our planet. The truth is, we don't know for sure if other planets have active plate tectonics in the same way we do. Venus shows signs of past resurfacing, and Mars has some immense volcanoes, but nothing on the scale of Earth's dynamic, moving crust. This raises a fundamental, unanswered question. Is plate tectonics essential for a planet to remain habitable over billions of years? Or is it just a happy coincidence that we have it? The harmony of all these factors, the right distance from the sun, the presence of liquid water, a protective atmosphere, a strong magnetic field, and an active geological system, is often called the Goldilocks principle. The idea that everything is just right. It is a delicate and improbable balance. Even a slight change, a shift in our orbit, a change in our star's output could dramatically alter our planet's fate. We are like a small boat on a vast ocean, navigating a cosmic sea with an incredibly fine-tuned set of instruments. It is this precariousness that makes our world all the more precious. As we look at our planet from the outside, we see a world that is not just a rock with an atmosphere. We see a living, breathing entity, a complex system of interconnected parts. We see the swirling white of clouds, the deep, calming blue of the oceans, and the varied greens and browns of the continents, all dancing in a cosmic ballet. It is a world of immense history and untold potential. And it is a constant reminder that for all our travels to other planets, for all our wonder at the distant stars, the most profound mystery of all may be the one we are standing on. How did we get here? Why does this one particular rock in this one particular solar system pulse with such vibrant, undeniable life? The answer remains one of the great unknowns. We have looked at Earth, a world teeming with life, and now we will turn our attention to its constant companion, a silent witness to our history and a powerful force in our lives. We're talking, of course, about the moon, It's a world of stillness and memory, a place that seems so familiar from our night sky, yet holds deep mysteries about its violent birth and its profound, patient influence on our own planet. To understand the moon is to understand a part of ourselves, for our fates have been intertwined from the very beginning. The most widely accepted theory for the moon's formation is a dramatic one, a story of cosmic collision. Around 4.5 billion years ago, just after Earth had formed, a Mars-sized body, sometimes called Theia, slammed into our young planet. This wasn't a glancing blow, but a cataclysmic impact. The immense energy of the collision melted both bodies, and the debris, a mixture of rock and molten material from Earth's outer layers, and Theia itself, was ejected into orbit around Earth. Over time, this ring of fiery debris coalesced, a process of accretion similar to how the planets formed, only on a much smaller scale. It cooled and solidified, and our moon was born. This theory, known as the giant impact hypothesis, helps explain several key facts about the moon. Firstly, the moon's density is much lower than Earth's. This makes sense if it was formed mostly from Earth's less dense outer crust and mantle, leaving behind the heavy iron core of Theia, which would have sunk into our planet's own core. Secondly, the chemical composition of lunar rocks is surprisingly similar to rocks from Earth's mantle, but with key differences. They are depleted in what are called volatiles, elements and compounds that have low boiling points like water. This suggests that the intense heat of the impact boiled them away, a detail that the hypothesis beautifully accounts for. The moon's surface is a testament to its ancient, unchangeable nature. Unlike Earth, which has a dynamic, constantly recycling surface, the moon is a geological fossil. It has no atmosphere to erode its features, no liquid water to smooth its craters, and no plate tectonics to bury its past. It is a world of stillness, where a footprint left by an astronaut will remain for millions of years. This lack of geological activity makes the moon a perfect record keeper of the solar system's early chaotic period of bombardment. Every crater, every basin is a scar from a long-lost collision, a story written in stone. The dark patches we see on the moon, which we once imagined to be seas or oceans, are in fact vast plains of ancient solidified lava, a testament to the fact that the moon was once volcanically active, but its internal engine has long since cooled and stopped. A lesser-known fact about our moon is its profound effect on life on Earth. Its gravitational pull is what creates the tides in our oceans, a constant, rhythmic tug that has shaped coastlines and created a rich biodiversity in our intertidal zones. But its influence extends far beyond this. The moon's gravity also acts as a stabilizer for Earth's axial tilt. Our planet is tilted on its axis at about 23.5 degrees, which is what gives us our seasons. Without the stabilizing presence of our large moon, Earth's tilt would wobble and shift dramatically over time, leading to extreme and erratic climate changes that would have made the evolution of complex life much more difficult. The moon is not just a pretty object in the night sky. It is a fundamental part of the complex system that makes Earth habitable. The truth is, we don't really know if our moon's formation was a unique event in the universe. Is it common for terrestrial planets to have such a large, stabilizing satellite? It's a beautiful question, one that is crucial to the search for life on other worlds. If a large moon is a prerequisite for long-term climate stability, and thus for the evolution of complex life, then perhaps we are even more rare and precious than we think. As we look at the moon, we see a world of profound silence and deep cosmic history. We see the scars of ancient battles, the echoes of a long-lost past. We see a mirror reflecting our own fragility and the immense forces that have shaped our existence. It is a world that seems so close, so intimately connected to us. Yet, it is a quiet, desolate place, a reminder of the universe's powerful indifference. We have walked on its surface, and we have brought back its rocks. But the full story of the moon, its ultimate purpose, and its place in the grand scheme of things, is still a beautiful mystery. It is a constant invitation to look up, to ponder, and to appreciate the fragile, chaotic, and beautiful dance of our own home. We have left the silent, rocky stillness of the moon and are now moving away from the inner solar system, leaving behind the warmth of the sun. As we travel, the light softens, and the cosmic dust we once imagined as a fiery forge becomes a cool, drifting memory. Our next destination is a world of echoes and ghosts, a place of faded oceans and a quiet, persistent hope. We are arriving at Mars, the red planet. From Earth, Mars shines with a distinct reddish hue. This color comes from the iron-rich dust that covers its surface, dust that has rusted over billions of years. To the ancients, this color was a symbol of war, and they named it after their god of war. Yet the Mars that we know today is not a place of violent conflict, but a world of profound loneliness. It is a world that seems to be trapped in a deep planetary sleep, a dream of what it once was. Mars is a world of stark and beautiful features. It is home to Olympus Mons, the largest volcano in the solar system, a colossal mountain that stands over 13 miles high, 3 times the height of Mount Everest. Its immense size is a testament to the fact that Mars lacks plate tectonics. Without the slow grinding movement of a dynamic crust, volcanic hotspots remained fixed in place, allowing lava to build up over eons, creating mountains on an almost unimaginable scale. The planet also has valles marineris, a canyon system so vast it would stretch across the entire United States, a scar on its surface that whispers of past geological upheaval. But the most compelling feature of Mars is the unmistakable evidence of water. Spacecraft and rovers have found dry riverbeds, deltas, and floodplains, all carved by a liquid that no longer flows. We have found ancient lake beds and minerals that only form in the presence of water. It is a fact that in the distant past, Mars was a warmer, wetter world with a thicker atmosphere, rivers that flowed to seas, and a potential for life that we can only dream of. The question, of course, is what happened. The leading theory is that as Mars, being a smaller planet than Earth, cooled down, its core solidified. This caused its magnetic field to weaken and eventually disappear. Without a protective magnetosphere, the relentless solar wind stripped away Mars's atmosphere, molecule by molecule. As the atmosphere thinned, the pressure dropped, and the water either evaporated into space or froze into the ground. This process, known as atmospheric stripping, is a key concept in planetary science, and Mars is its most tragic example. A planet can have all the right ingredients for life: liquid water, a protective atmosphere, but if its core can't sustain a magnetic field, it's all for naught. The thin, tenuous atmosphere that remains on Mars today is a shadow of its former self, a silent monument to what was lost. The pressure is so low that if you were to stand on the surface without a spacesuit, any liquid water you had would immediately boil away. A fascinating and somewhat eerie fact about Mars is the presence of strange, recurring slope lineae. These are dark streaks that appear on some Martian slopes in the spring and summer and then fade in the autumn and winter. While their exact cause is still debated, some scientists believe they are caused by briny or salty water flowing down the slopes, a last ghost of the planet's liquid past. The existence of even small transient flows of water raises a profound philosophical and scientific question. Could there still be life on Mars? Perhaps in a protected subterranean environment, or in the form of dormant spores waiting for a time that will never come. The search for this life, past or present, is the central goal of our missions to the Red Planet. The truth is, We don't know for sure if life ever existed on Mars. The evidence we have is tantalizing, but not conclusive. And this lack of a definitive answer makes the planet all the more compelling. It is a beautiful puzzle, a mystery that draws us in with its promise of discovery. The dream of one day walking on Mars, of digging into its rusty soil and finding a single fossilized cell, is one of the grandest human ambitions. It is a dream that speaks to our deep, innate curiosity about our place in the universe. Is life a unique occurrence on our small blue dot? Or is it a common, persistent force that will find a way to take hold wherever it can? Mars is the first place where we might find the answer. We leave Mars now, a world of beautiful canyons and haunting, empty plains. It is a world of potential and loss, a silent echo of a life that may have been. And as we leave, we can't help but feel a quiet sense of sadness for a world that seems to have just missed its chance. But it also gives us a profound appreciation for the fragile, vibrant life we have here. A precious anomaly in a universe of silent, desolate worlds. We have left the small, silent worlds of the inner solar system behind. The red echoes of Mars are now just a memory. And as we travel farther from the sun, a new reality begins to assert itself. The warmth of our star becomes a faint, distant glow, and we enter a realm of immense scale and unbelievable power. We are now approaching the true giant of our cosmic neighborhood, Jupiter. Jupiter is a colossus. It is so large that its mass is more than twice the mass of all the other planets in our solar system combined. It is a world without a solid surface, a churning, swirling sphere of hydrogen and helium, held together by its own immense gravity. It is a world of incredible speed and violence, where storms larger than Earth have raged for centuries, and winds blow at speeds of hundreds of miles per hour. The most famous of these storms is, of course, the Great Red Spot. This isn't just a storm. It's an anticyclonic storm, a high-pressure system that has been observed for at least 350 years. We don't know for sure why it has lasted so long, but we do know that its sheer size is staggering. At its widest, it is large enough to swallow Earth whole. It is a testament to the sheer energy and raw power of Jupiter's atmosphere, a system so vast and so dynamic that it operates on a different scale entirely from anything we know. Jupiter's appearance, with its distinct bands of swirling clouds, is a result of a process called zonal flow. The planet's rapid rotation, a single day on Jupiter is only about 10 hours long, creates powerful currents in its atmosphere that separate the clouds into light and dark bands. The lighter bands are called zones and are thought to be areas of rising, cooler gas, while the darker bands are called belts and are areas of sinking, warmer gas. This constant movement, this endless churning, is the very heartbeat of the gas giant. One of the more fascinating and lesser-known facts about Jupiter is that it has a solid core, but not in the way we think of one. Scientists believe that deep within the planet, under unimaginable pressure, the hydrogen gas transforms into something else entirely, a state of matter known as metallic hydrogen. It's a liquid, and it conducts electricity like a metal. This bizarre, swirling sea of metallic hydrogen is the source of Jupiter's incredibly powerful magnetic field, a field that is nearly 20,000 times stronger than Earth's. This magnetic field is Jupiter's shield, much like Earth's magnetosphere. It deflects the solar wind and creates a massive radiation belt that is thousands of times more powerful than the Van Allen belts that surround our own planet. The radiation is so intense that any spacecraft flying through it would need to be heavily shielded. The power of this magnetic field extends far beyond Jupiter itself. It is a massive cosmic net, trapping charged particles and creating beautiful aurora at the planet's poles, lights that are hundreds of times brighter and more powerful than our own. Jupiter's role in our solar system goes beyond its size and beauty. It is an ancient guardian, Its immense gravity acts as a cosmic vacuum cleaner, a gravitational bouncer, pulling in or deflecting dangerous comets and asteroids that could otherwise pose a threat to the inner planets, including Earth. It is a silent protector, a force of nature that has likely saved our planet from countless cataclysmic impacts throughout its history. The truth is, we don't know for sure what our solar system would look like without Jupiter. Would life have had the chance to evolve without its protective presence? It's a beautiful, unanswerable question. We leave Jupiter now, but its moons are a universe unto themselves. We will not explore them in detail here, but it is worth noting that they are some of the most compelling places in the solar system. Io, a world of constant volcanic eruptions, is a testament to the powerful tidal forces of its host planet. Europa, a world with a vast, subsurface ocean of liquid water, holds the tantalizing promise of life. And Ganymede, the largest moon in the solar system, is a world with its own magnetic field. These moons are not just passive companions. They are active, dynamic worlds, each with its own story to tell, all under the watchful, gravitational gaze of the great giant. Jupiter is a constant reminder of the scale of the cosmos. It is a world of chaos and order, of immense power and quiet protection. It is a world that seems so alien, so different from our own. Yet it is intimately tied to our history and our fate. It is a world of beautiful, swirling clouds and an invisible, powerful force that keeps us safe. It is a true king of our solar system and a constant source of wonder. We have traveled past the immense, swirling chaos of Jupiter, the solar system's silent guardian. The scale of the gas giant is now a powerful memory, but the cosmos has more beauty to reveal as we journey outward. Our next destination is a world of quiet elegance, a true jewel of the solar system, known for a feature that has captivated human imagination for centuries. We are arriving at Saturn. Saturn is a gas giant, much like Jupiter, but it is defined by its rings. From Earth, they appear as a solid continuous halo, but they are in fact a vast, intricate system of countless icy particles, ranging in size from a grain of sand to a house. These particles are not attached to the planet. They are all orbiting Saturn independently, like billions of tiny moons in a complex and delicate dance. If we could somehow gather all the material in Saturn's rings and compress it, the resulting body would likely be less than 60 miles across, a surprisingly small amount of mass for a feature so grand. The rings themselves are a perplexing puzzle. How did they form, and why are they so pristine? One leading theory suggests that they are the remains of a moon, perhaps a small icy satellite that wandered too close to Saturn and was torn apart by the planet's immense tidal forces. This event, which would have been a cosmic cataclysm, would have scattered the moon's debris into a disk around the planet, where it has remained ever since. However, a lesser-known fact about Saturn's rings is that they are thought to be quite young, perhaps only 100 million years old. This is a very short time in the history of our solar system, which is 4.5 billion years old. The youth of the rings raises a profound question. If they are so young, what destroyed the moon and created them? And are they a temporary, fleeting phenomenon, or a sign that Saturn is constantly acquiring new ring material? The truth is, we don't know for sure, and this puzzle is a central topic of ongoing research. Saturn itself is a world of subtle beauty. Its atmosphere is a mix of hydrogen and helium, much like Jupiter's, but its bands are far less distinct, giving it a soft, golden hue. Winds on Saturn can reach supersonic speeds, over 100 miles per hour at its equator, but its overall appearance is one of tranquil serenity. Deep within its core, under crushing pressure, it is believed to have a solid, rocky core, a dense heart at the center of a swirling gaseous ocean. This core, and the liquid metallic hydrogen layer above it is the source of Saturn's powerful magnetic field, a force that, like Jupiter's, protects the planet and its many moons from the solar wind. Speaking of moons, Saturn has a vast family of them, a total of 146 confirmed satellites. They are a menagerie of bizarre, unique worlds. Titan, the largest, is a world with a dense, nitrogen-rich atmosphere, thicker than Earth's, and a surface with liquid methane lakes and rivers. It is the only moon in the solar system known to have a substantial atmosphere. Another moon, Enceladus, is a small icy world that spews plumes of water vapor and ice from its south pole, a clear sign of a subsurface ocean of liquid water and active cryovolcanism. This raises the tantalizing possibility of life as we know it, hiding beneath its frozen crust. The intricate relationship between Saturn's rings and its moons is a beautiful example of celestial mechanics. Some of Saturn's smaller moons, known as shepherd moons, orbit on either side of the rings, and their gravitational pull helps to keep the ring particles in their place, preventing them from spreading out and dissipating. These moons, like Atlas and Prometheus, are tiny gravitational shepherds, corralling the billions of icy particles and preserving the elegant form of the rings. It is a subtle, intricate dance, a reminder that even in the chaos of space, there is a beautiful underlying order. As we leave Saturn, we are left with a sense of its quiet, majestic presence. It is a world of contradictions, of fleeting, young rings and an ancient, stable core, of supersonic winds and a serene, beautiful exterior. It is a world that, in its silent, graceful orbit, teaches us that beauty can be found in the smallest of things, from a tiny grain of ice to a colossal ring system. The rings of Saturn are not just a spectacle. They are a beautiful, unsolved puzzle, a cosmic question mark suspended in the inky blackness. We have left the tranquil elegance of Saturn and are now journeying to the final frontier of our solar system's inner family. The light of the sun is now a distant point, a star among stars, and the warmth it provides is a thing of the past. Our next destination is a world that truly stands apart, a planet of mystery, a tilted wanderer. We are arriving at Uranus. Uranus is a world of quiet paradox. To the naked eye from Earth, it is a faint, uninspiring dot, the first planet discovered with a telescope. Its beauty is subtle, and its atmosphere is surprisingly featureless. Unlike the vibrant, swirling clouds of Jupiter and Saturn, Uranus appears as a serene, blue-green orb. This color comes from the methane in its atmosphere, which absorbs red light and reflects blue and green. It is an ice giant, a different class of planet from its gas giant cousins, with a solid core and a thick mantle of water, methane, and ammonia ices under immense pressure. But the most distinctive and perplexing thing about Uranus is its orientation. While all the other planets in our solar system spin more or less upright, like tops, Uranus is tilted on its side. Its axis of rotation is nearly parallel to its orbit, meaning it effectively rolls around the sun like a ball. This gives it the most extreme seasons in the solar system. For a quarter of its long 84-year orbit, one pole is pointed directly at the sun, while the other is plunged into a quarter century of complete darkness. This poses a fundamental question. What kind of cataclysmic event could have caused this? The leading theory is that a massive Earth-sized object slammed into the young Uranus billions of years ago, knocking it over and forever changing its trajectory. This idea, like the giant impact hypothesis for our moon's formation, reminds us of the sheer violence and chaos of the early solar system. A lesser-known fact about Uranus is its incredibly cold temperatures. Despite its extreme tilt and the fact that one side faces the sun for decades, it is the coldest planet in the solar system. The lowest temperature ever recorded in its atmosphere was a chilling minus 371 degrees Fahrenheit. Why is it so cold? Scientists believe that the impact that knocked it over also might have stripped away its internal heat. The planet radiates very little heat from its core, unlike its companions, Jupiter and Saturn, which both have powerful internal heat engines. This lack of an internal heat source is likely the reason why its atmosphere is so calm and featureless. Without the rising heat to create massive convection currents, there is very little atmospheric motion, creating a world that is, on the outside, a picture of tranquil, frozen serenity. The lack of an internal heat source and the extreme tilt lead to a beautiful and still debated scientific puzzle. We would expect the sunlit side of Uranus to be significantly warmer than the dark side, given the decades of continuous sunlight. But surprisingly, measurements show that there is very little temperature difference between the two sides. This suggests that some unknown mechanism is efficiently distributing the heat across the entire planet. What this mechanism is, we don't know for sure. This raises a fascinating, unanswered question that speaks to the heart of atmospheric dynamics. How can a planetary atmosphere so effectively distribute heat from one end to the other? Despite its lack of an obvious energy source, Uranus also has a faint ring system, though it is nowhere near as magnificent as Saturn's. Its rings are thin and dark, made up of dust and small rocky particles. And it has a family of 27 known moons, all named after characters from the works of Shakespeare and Alexander Pope. These moons are also tilted on their sides, orbiting the planet's equatorial plane, a silent testimony to the colossal event that once changed the entire system's orientation. We leave Uranus now, a world that is a beautiful mystery. It is a planet that teaches us that even in our solar system, with its seemingly familiar rules, there can be worlds that defy our expectations and challenge our theories. The silent, blue-green orb, rolling slowly through the blackness of space, is a testament to the fact that there is still so much we do not know, and that the universe holds secrets waiting to be uncovered. We have left the puzzling tilt of Uranus and are now continuing our deep space journey into the final frontier of our solar system's planetary family. The sun is no longer a bright disk, but just the brightest star in the night sky, and the cold of space is a physical presence. Our destination is a world of fierce winds and beautiful fleeting clouds, a distant blue heart. We are arriving at Neptune. Neptune is the 8th and final official planet in our solar system, a world of deep, ethereal blue. Like Uranus, it is an ice giant, a world of hydrogen, helium, and methane ice surrounding a rocky core. But unlike Uranus, Neptune is not a calm, serene orb. It is a world of violent winds, the fastest in the solar system, with speeds that can reach over 1,500 miles per hour, more than twice the speed of sound. This begs a question. How can a world so far from the sun, a place that receives so little energy, generate such powerful atmospheric forces? This is one of the great mysteries of Neptune. One of the more fascinating and lesser-known facts about Neptune is its active weather systems. When the Voyager 2 spacecraft flew past Neptune in 1989, it discovered a massive storm system called the Great Dark Spot, a storm the size of Earth, which appeared as a large, swirling vortex in the planet's southern hemisphere. This storm was a mirror image of Jupiter's Great Red Spot, a vortex of high pressure. But when the Hubble Space Telescope later looked at Neptune, the Great Dark Spot was gone. It had simply dissipated, leaving no trace. This suggests that Neptune's weather patterns are not as stable and long-lasting as those on Jupiter, but are instead beautiful, powerful, but fleeting phenomena. The fact that a storm of that size could just disappear is a profound and humbling reminder of the dynamic, ever-changing nature of planetary atmospheres. The brilliant blue color of Neptune comes from the same source as Uranus's, the small amount of methane in its atmosphere that absorbs red light. But Neptune's blue is a much deeper, more saturated hue, a mystery that scientists believe may be due to the presence of some unknown atmospheric component, perhaps a cloud of a different kind of ice, or some other photochemical reaction is at play. The truth is, we don't know for sure, and this puzzle is a beautiful example of how even simple, seemingly cosmetic differences between two similar worlds can point to deep, fundamental differences in their composition and history. Neptune's winds are a testament to its internal heat. Unlike the cold, dead core of Uranus, Neptune's core is believed to be quite warm, radiating a great deal of internal energy. This energy drives the immense atmospheric convection currents that create those supersonic winds. It is a world that seems to be in a constant state of turmoil, with winds that circle the planet faster than its rotation. Neptune has a small family of 14 known moons, but one of them stands out as a world of particular fascination. Triton, Neptune's largest moon, is a world of icy geysers that spew plumes of nitrogen gas and dust hundreds of miles into space. It has a retrograde orbit, meaning it orbits in the opposite direction of Neptune's rotation, a clear sign that it was not formed in place, but was instead a captured object, likely from the Kuiper Belt. The idea of a rogue world, an icy wanderer from the outer solar system, being captured by the gravitational pull of a giant and then being forced into a new endless dance, is a poetic one. Neptune is a world of beautiful contradictions. It is a planet of incredible chaotic power, a place of supersonic winds and massive transient storms. Yet it is also a world of quiet, ethereal beauty, a deep blue orb at the very edge of our planetary family. It is a final act in a grand cosmic play, a world of mystery and power, and a reminder that even at the very edge of our cosmic neighborhood, there is still so much to discover. It is a beautiful, distant heart, beating with a powerful, hidden energy. We have left the beautiful, stormy world of Neptune and are now drifting into a region that feels more like the true edge of our cosmic neighborhood. The planets as we know them are behind us, and we are entering a new, cold and dark realm. This is the Kuiper Belt, a vast ring of icy bodies, and at its heart lies a world that once held the title of a planet, a small, solitary wanderer. We are arriving at Pluto. For over 70 years, Pluto was known as the ninth planet of our solar system, a distant, enigmatic world at the very edge of our family. But in 2006, after the discovery of several other large icy bodies in the same region, the International Astronomical Unions reclassified Pluto as a dwarf planet. This decision sparked a great deal of controversy, with many people feeling a sense of loss for the tiny, beloved world. But the reclassification was not an insult. It was a refinement of our understanding. It taught us that Pluto is not a solitary planet, but a member of a much larger and more numerous family. Pluto is a world of incredible beauty and surprising complexity. From the images sent back by the New Horizons spacecraft, we see a world with a vast, heart-shaped glacier of frozen nitrogen and methane, surrounded by rugged, icy mountains that are believed to be made of water ice. The surface is a mix of bright, young terrain and older cratered regions, suggesting that Pluto, despite its small size, is geologically active. It is a world with a thin, tenuous atmosphere that expands and contracts as it gets closer to and farther from the Sun in its long elliptical orbit. When it is at its closest point to the Sun, the surface ice warms and sublimates into a gas, creating a thin atmosphere. As it moves away, the atmosphere freezes and collapses back onto the surface. This is a beautiful seasonal cycle that happens over a period of 248 Earth years. One of the more fascinating and lesser-known facts about Pluto is its system of moons. It has 5 of them, with the largest, Charon, being so massive in comparison to Pluto, it's about half Pluto's size, that the 2 bodies are often considered a binary system. They orbit a point in space between them, a gravitational dance that is unique in our solar system. Charon is a world of its own, with a distinct red cap at its pole and a system of canyons that dwarfs our own Grand Canyon. The complex, synchronized orbit of these 2 worlds is a beautiful testament to the power of gravity, even at the very edge of our solar system. The reclassification of Pluto, while initially disappointing to some, actually opened up a new realm of discovery. It made us realize that the Kuiper Belt, the region beyond Neptune, is a vast, populated realm. This raises a new question, one that speaks to the very heart of planetary science. Where does a planet end and a dwarf planet begin? There is no clear definitive line. The truth is, we don't know for sure how many of these icy, distant worlds are out there. The Kuiper Belt is a treasure trove of these dwarf planets. Some of them, like Eris and Haumea, are nearly the size of Pluto. The discovery of these worlds is a reminder that our understanding of the solar system is not a finished book, but an ongoing story. As we leave Pluto, we are left with a new perspective. It is not a lonely, lost world, but the magnificent king of a hidden realm. It is the beginning of our understanding of the outer solar system, a gateway to a vast, mysterious region that we have only just begun to explore. Its heart-shaped glacier and its beautiful, chaotic family of moons are a testament to the fact that even at the very edge, in the coldest and darkest parts of our cosmic neighborhood, there is still wonder to be found. We have ventured into the Kuiper Belt, a vast, dark realm of icy bodies and dwarf planets, with Pluto as its most famous resident. As we leave this frozen territory, we are only just beginning to touch upon the true scale of our solar system. The planets, as we know them, are now impossibly small points of light in the distance, and the sun itself is just one bright star in a tapestry of billions. Our journey continues outward to the most distant, unexplored regions of our solar system, to the Kuiper Belt and the even more remote Oort Cloud. The Kuiper Belt is not a tidy, narrow ring like the asteroid belt between Mars and Jupiter. It's a vast, donut-shaped region of space that extends far beyond Neptune's orbit, from about 30 to 55 astronomical units from the Sun. An astronomical unit, or AU, is the average distance from the Earth to the Sun, about 93 million miles. So, we're talking about a space so immense, a distance so staggering, that it defies easy comprehension. This region is a leftover from the formation of our solar system, a cold storage of primordial material, mostly small icy bodies, frozen remnants of the very cloud that gave birth to our star and its planets. The objects in the Kuiper Belt, like Pluto and its fellow dwarf planets, are called trans-Neptunian objects, or TNOs. They are slow-moving, quiet worlds with incredibly long orbits. Some of them, like the dwarf planet Haumea, spin so fast that they are shaped like an egg, a result of a past collision. Another Make is so far away that we know very little about it, except that it is a small, cold, red world. A lesser-known fact about the Kuiper Belt is that it is believed to be the source of many of the short-period comets, those comets that orbit the Sun in less than 200 years. Occasionally, the gravitational pull of Neptune or another passing object will nudge a Kuiper Belt object out of its quiet orbit and send it on a long, arcing journey toward the inner solar system, where the Sun's heat causes its ice to sublimate, creating a beautiful tail that we can see from Earth. But even the Kuiper Belt is not the true edge of our solar system. Beyond it lies a vast, theoretical sphere of icy bodies that is believed to surround our Sun like a gigantic ghostly bubble. This is the Oort Cloud, a cometary nursery that is so far away it's on the very fringe of the Sun's gravitational influence. We have never seen the Oort Cloud, and we may never be able to. Its objects are too small and too far away to be observed directly. Its existence is a theoretical hypothesis, based on our observations of the long-period comets, those with orbits of thousands or even millions of years. These comets, like Halley's Comet, seem to come from every direction in space, suggesting that their source is not a flat disk, like the Kuiper Belt, but a vast spherical cloud that extends to a distance of 5,000 to 100,000 AU from the Sun. To put this distance into perspective, if the solar system were the size of a dinner plate, the Oort Cloud would be a sphere with a diameter of over 2 football fields. We are now talking about a scale that transcends our everyday experience. The nearest star, Proxima Centauri, is only a quarter of the way through the Oort Cloud from our perspective. It is a region of space so cold and so dark that atoms themselves are at a near standstill. The objects within it are a collection of cosmic frozen watermelons, as they have been called, small icy bodies that have remained unchanged since the very birth of our solar system. This raises a beautiful and unanswerable question. What kind of secrets do these ancient cometary nuclei hold? The truth is, we don't know for sure. They are untouched relics from a time before the planets had even finished forming. They are time capsules, waiting to be studied. They represent a fundamental puzzle in our understanding of our solar system's origins. Are they a leftover from our sun's birth, or did they come from other stars? Scientists believe that the Oort Cloud may be a mix of both, a cosmic melting pot of matter gathered from our sun's journey through its stellar neighborhood. As we journey through this deep space wilderness, we are reminded that our solar system is not just the 8 planets we know and love. It is a vast, interconnected system of stars, dust, and ice that stretches far beyond our current view. We are only just beginning to scratch the surface of this cosmic home, and the silent whispers of the Kuiper Belt and Oort Cloud are a constant reminder that the universe is far more complex and beautiful than we can possibly imagine. We have journeyed to the true edge of our solar system, to the vast, cold realms of the Kuiper Belt and the Oort Cloud. We have seen how our cosmic home is far larger and more mysterious than we ever imagined. Now, as we begin to turn our gaze inward again, we must consider the invisible force that has guided our entire journey. We must contemplate the grand architect of our solar system, the silent, powerful weaver of all things. We are talking about gravity. Gravity is the fundamental force that binds everything together. It is the reason the sun ignited, the reason the planets formed, and the reason they all dance in their precise, clockwork orbits. For centuries, our understanding of gravity was defined by Sir Isaac Newton. His law of universal gravitation, published in 1687, was a beautiful and elegant equation. It stated that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. In essence, the more massive two objects are, and the closer they are to each other, the stronger the pull between them. This explained the orbits of the planets with stunning accuracy. It was a masterpiece of physics, a testament to the idea that the universe was governed by simple, elegant rules. But in the early 20th century, a young Albert Einstein came along and changed our understanding of gravity forever. He didn't disprove Newton, but he provided a deeper, more profound explanation. Einstein's theory of general relativity proposed that gravity is not a force that pulls, but a consequence of the curvature of space and time. He said that a massive object, like a star or a planet, warps the fabric of space-time around it, much like a bowling ball placed on a stretched rubber sheet. Other objects, like planets or moons, don't feel a pull from the massive object. They are simply following the shortest, most natural path through that curved space-time. This is a beautiful and counterintuitive idea. It means that the planets aren't being tugged on by the sun. They are simply following the curves and valleys that the sun has created in space-time. The Earth is not circling the sun because of a mysterious force pulling it, but because it is trapped in the sun's gravitational well, rolling along the curved fabric of existence. A lesser-known fact about general relativity is that it predicts that gravity can actually bend light. This was a radical idea, but it was proven correct during a solar eclipse in 1919 when astronomers observed that the light from distant stars was indeed bent by the sun's immense gravity, appearing slightly out of place. This observation confirmed Einstein's theory and cemented his place in history. The philosophical implications of this are immense. Gravity is not a force, but the very geometry of the universe. It is a quiet, powerful presence that is inseparable from the very fabric of existence. This raises a beautiful and unanswerable question. Is space-time a physical thing? Something we could one day feel or touch? Or is it just a mathematical construct, a beautiful way of describing a deeper underlying reality that we may never truly understand? The truth is, we don't know. The journey we have taken, from the birth of a star to the distant icy moons of the outer solar system, has been a journey through gravity's art. We have seen how it sculpted planets from a diffuse cloud, how it holds the moon in its dance with Earth, and how it keeps the gas giants as silent protectors. It is a force that is at once immense and subtle. It is what keeps us from flying off into space, and it is what keeps the galaxies from flying apart. As we end this chapter, we are left with a new perspective on our universe. It is not just a collection of objects floating in a void, but a beautiful, interconnected tapestry woven by an invisible force. The planets, the moons, the comets, and even the light from a distant star are all bound together in a quiet, cosmic ballet. And the choreographer of that ballet, the silent, patient artist, is gravity itself. It is the very foundation of our cosmic home, and it is the quiet, constant force that reminds us of our place in the grand scheme of things. We have contemplated the beautiful, invisible force of gravity, the weaver of our cosmic tapestry. It is a force that reminds us that everything is connected. Now we must consider another dimension of our journey, one that is as vast and as fundamental as space itself. We will turn our attention to the great cosmic clock, to the concept of time. In our daily lives, time feels like a simple, linear flow. A second, a minute, an hour. We use these units to measure our days. But in the context of the cosmos, time is a far more complex and mind-bending concept. Our journey through the solar system has been a journey through time as much as it has been a journey through space. The light from the sun takes a little over 8 minutes to reach Earth. The light from Jupiter takes over half an hour. The light from Pluto at its farthest takes over 5.5 hours. This means that when we look at the planets in the night sky, we are not seeing them as they are right now, but as they were in the past. We are looking back in time. This idea becomes even more profound when we consider the stars beyond our solar system. The nearest star, Proxima Centauri, is about 4.2 light-years away. A light-year is the distance that light travels in a year, a staggering 5.88 trillion miles. So, when we look at Proxima Centauri, we are seeing light that left that star 4.2 years ago. We are seeing it as it was in the past. The further we look into the universe, the further back in time we see. The James Webb Space Telescope can see galaxies that are over 13 billion light-years away, allowing us to peer into a time just after the universe was born. This is a beautiful and humbling fact. The universe is a cosmic time machine, and every time we look up, we are a time traveler. But time is not just a linear river. It can be warped and bent. Remember how we talked about Einstein's theory of general relativity? That theory not only tells us that gravity warps space-time, but also that it can slow down time itself. This is a concept known as gravitational time dilation. The closer you are to a massive object, the slower time passes for you relative to someone further away. For example, a clock on the International Space Station, which is orbiting Earth and experiencing a slightly weaker gravitational field, runs a tiny bit faster than a clock on the ground. This effect is so small that we don't notice it in our daily lives, but it is a real, measurable phenomenon. It is an essential component of the GPS satellites that guide us, as their clocks must be adjusted to account for the slower passage of time on Earth's surface. A lesser-known fact about time is the twin paradox, a thought experiment in special relativity. Imagine two identical twins. One stays on Earth, while the other travels on a rocket ship at a very high speed for a long journey. According to Einstein's theories, when the traveling twin returns, they will be younger than the twin who stayed on Earth. This is not science fiction. It is a direct consequence of time dilation. Time, as we experience it, is not absolute. It is relative to our motion and our position in a gravitational field. This raises a fascinating, unanswered question. Is time a fundamental property of the universe, or is it an emergent property, a consequence of something else? Is there a deeper underlying reality that gives rise to the flow of time? The truth is, physicists still wonder about this. We don't really know for sure if time is a river or an illusion. This is one of the most profound mysteries in all of science, a question that connects the immense scale of the cosmos with the most intimate parts of our own experience. Our journey through the solar system has been a reminder of the immense scales of both space and time. We have seen worlds that took millions of years to form, and we have seen light that has traveled for hours to reach us. We are living in a universe of deep history and a constant, invisible flow that we are only just beginning to comprehend. The passage of time is a beautiful, gentle current that carries us all, and it is a reminder that we are all part of a much larger story than we can possibly imagine. We have traveled a long way together. We've seen a lonely star's first breath, witnessed the fiery extremes of Mercury, and pondered the veiled dangers of Venus. We've stood on our fragile blue dot and marveled at the silent witness of the moon. We've crossed the great cosmic gulf to see the faded echoes of Mars and the immense, swirling majesty of Jupiter and Saturn. We've drifted past the quiet tilt of Uranus and the stormy beauty of Neptune. We've even ventured to the outer reaches, to the lost world of Pluto and the vast, mysterious cometary nurseries of the Kuiper Belt and the Oort Cloud. We have contemplated the silent, powerful force of gravity and the deep, mysterious river of time. This journey has been a story not just about planets, but about perspective. We began with a single cloud of dust and gas, and from that simple beginning, we have found a universe of incredible complexity. We have seen how location and chance, distance and circumstance can shape a world and determine its fate. We have seen that even in the vast emptiness of space, there is a beautiful underlying order, a cosmic dance governed by laws that are both elegant and strange. The solar system is a testament to the idea that from the simplest of ingredients, the most extraordinary things can arise. It is a story of creation, of destruction, of chance, and of a quiet, persistent beauty that fills the silence. We've learned that science is not just a collection of facts. It is a way of looking at the universe with a sense of awe and wonder. It is a series of questions, of beautiful, unanswered puzzles that keep us looking up at the night sky. We don't have all the answers, and that, in itself, is a source of great comfort. It means the story is not over. The universe is still full of secrets, waiting for us to discover them. The journey never truly ends. Now, as our journey comes to a close, I'd like you to gently bring your awareness back to where you are. Feel the soft texture beneath you, the quiet rhythm of your own breath, the vastness of space, the immense distances, the billions of years of cosmic history. All of that is now just a whisper. Let it all slowly fade. the fiery heat of Venus, the supersonic winds of Neptune, the silence of the moon. Let them all gently brush past you. Like soft clouds on a summer day, I want to gently ask one last time. Where is the place you're staying now? The time in that place, at this very moment, how is it flowing? You are here, right now, in this moment. You are a part of this beautiful living planet, and you are a part of this immense and wonderful universe. May the thoughts of distant worlds and cosmic history fill your mind not with anxiety, but with a deep sense of peace. Sleep well, my companion, wherever and whenever you are. May the quiet rhythm of the universe be your lullaby